You type a conversational question into a chat box and receive a highly sophisticated analysis in seconds. These outputs often mirror human reasoning, suggesting the presence of a digital researcher referencing an internal database of facts. However, the system operates without a relational database or a conceptual model of the world. Each response is generated without an underlying factual memory. A large language model functions as a high-dimensional statistical prediction engine. The architecture focuses on a single objective: calculating the mathematical probability of a specific sequence continuation. Controlling these tools requires viewing them as mathematical models rather than conversational partners. Microprocessors compute numbers, not language. To process a sentence, the system must first translate text into a format it can calculate. This translation layer is called tokenization. It converts human language into quantifiable mathematics. Take the phrase peanut butter and jelly. The system fractures the text into distinct subwords and punctuation. Each chunk is mapped to a unique integer ID within the vocabulary. The model processes these integer arrays exclusively, ignoring the original text. This numerical processing occurs within a space called the context window, which has a rigid physical limit. This grid represents the maximum number of tokens the system can hold in active memory. As we input data, the slots fill from left to right. When an input exceeds this capacity, the oldest integers are pushed off the grid to make room for new data. These dropped tokens are deleted from the current calculation. The model can no longer see that specific information. This data loss explains why a model might ignore early instructions or lose track of the beginning of a long conversation. Perceived forgetfulness is a result of this data truncation, which dictates how much context can be successfully processed at once. Once the tokens are secured in the context window, the model begins the process of generation. The engine uses a method called autoregressive generation to build its response. The system evaluates the existing sequence and calculates the statistical probability for every possible next token in its entire vocabulary. It ranks these possibilities, identifying the most likely mathematical continuation. The model selects the high probability token and appends it to the sequence. This new token loops back and joins the original input. The entire probability calculation then restarts to find the next token. This cycle repeats hundreds of times per second. The model operates without a plan for the final paragraph. It continues predicting until it reaches a specific stop token. The rapid chaining of these predicted integers creates the appearance of a cohesive, pre-planned thought. The system solves for the next fractional piece of a word in isolation, unaware of the larger narrative it is constructing. A language model learns to generate these accurate probability distributions through a process of massive, continuous data ingestion. Engineers use a mechanism called masked language modeling to train the foundational weights. The process starts with a verified sequence of text from the training data. A specific token in the sequence is hidden, creating a gap for the model to fill. The untrained model attempts to guess the hidden integer based on the surrounding context. A loss function measures the distance between the incorrect guess and the true token, producing an error score. This score sends a signal backward through the neural network. This signal, called backpropagation, adjusts millions of internal node weights to reduce the likelihood of that specific error in the future. This cycle of guessing, measuring, and adjusting occurs billions of times across terabytes of data. Over months of intensive computation, these continuous adjustments shape the internal math to align with the structures of human language. Training is the mechanical optimization of statistical weights, ensuring the model's outputs mirror the patterns found in its training data. This mathematical framework explains the system's tendency to produce false information. Hallucinations occur when the predictive logic prioritizes linguistic structure over factual accuracy. When training data is sparse, the probability of the correct token may drop to 0, while grammatically plausible tokens remain high. The engine selects the most likely syntax, completing the sentence even if factual probability is non-existent. The system optimizes for a structurally perfect response, even when it lacks the data to provide a truthful one. These errors are the result of a probabilistic engine prioritizing syntax over validity, requiring careful human verification. Understanding these mechanics allows users to influence the model's probability paths more effectively. Prompting is the application of mathematical constraints to a probability space. A prompt acts as a boundary, cropping out low probability paths to focus the model. Vague prompts provide loose constraints, leading to chaotic distributions, but highly specific prompts narrow the mathematical options, forcing the engine into a focused, laser straight line. Large language models operate by predicting patterns across large-scale datasets. Using AI effectively in a professional setting requires moving past the appearance of intelligence and mastering the underlying mechanics of probability.